Hello, in this video we're going to walk through solutions to a practice AP Calculus BC exam for the 2020 format. If you'd like to try taking the exam on your own before looking at these solutions, you can find a download link in the description below. For question 1, we're told that a function f has derivatives of all orders for all real numbers x. A portion of the graph of f is shown below, along with the line tangent to the graph of f when x equals 6, and selected derivatives of f are given in the table below. Part A of this question says, let g of x equal the integral from 3 to x f of 2t dt. Write the fourth degree Taylor polynomial for g about x equals 3. So let's start by writing the fourth degree Taylor polynomial for g in general. So that'll be p sub 4 of x, our constant term, just g of 3, divided by 0 factorial, but that's just 1, times x minus 3 to the power 0, but that's also just 1, so I'm not going to write that. Then for our linear term, it's g prime of 3 over 1 factorial times x minus 3 to the power 1. The next term, g double prime of 3 times x minus 3 squared. Then g triple prime, oh, I forgot my factorial. We got to divide that by 2 factorial. G triple prime of 3 over 3 factorial times x minus 3 cubed. And then finally, our fourth degree term would be the fourth derivative of g evaluated at x equals 3 over 4 factorial times x minus 3 to the power 4. So now we have to go back and find all of these coefficients, g of 3, g prime of 3, g double prime of 3, and so on. And to do that, we are going to use this equation for g here. And we'll start with just writing down g of x. So g of x is equal to the integral from 3 to x f of 2t dt. And we want g of 3. So g of 3 would equal the integral from 3 to 3. And really I can stop right there because I know if I integrate from 3 to 3, that's just going to equal 0, but I'll finish writing it out. Equals 0. Okay, so that coefficient for g of 3 will be 0. And then let's find g prime of x by taking the derivative of the integral of f of 2t dt from 3 to x. And to do that, we're using the fundamental theorem of calculus. So we get f of 2x times the derivative of x, which is just 1. And that means that g prime of 3, when we substitute 3 in for x, is just equal to f of 6. And f of 6 we can read right from the graph, f of 6 equals 0. Now g double prime of x is the derivative of f of 2x. We need to use the chain rule here. This is f of stuff. The derivative of f of stuff is f prime of stuff times the derivative of the stuff. Then we substitute in 3. So we get 2f prime of 6. Now f prime of 6 we can also find from the graph. F prime of 6 would be the slope of the graph at 6, which is also the slope of the tangent line at 6. And so we can just, starting at this point, rise over run, see that the slope there is equal to 2. So 2 times 2 gives us 4 for g double prime of 3. The third derivative will be 2 times the derivative of f prime of 2x. So the derivative of f prime of stuff is f double prime of stuff times the derivative of the stuff times the constant multiple that was already there. And g triple prime of 3 will be 4 f double prime of 6. F double prime of 6 we can read from the table. That's equal to 3, and 4 times 3 gives us 12. And then finally, the fourth derivative of g will be the third derivative of f of 2x times 2 times the 4 that's already there. And then the fourth derivative of g when x equals 3 will be 8 times f triple prime of 6, and that we get from the table is negative 2. So this is negative 16. Okay, we have our coefficients now. So we've got our 0, 0, 4, 12, and negative 16, and those are going to get substituted in for our g of 3, g prime of 3, g double prime of 3, and so on. Those values right there. And the first two values are 0, so we can ignore these first two terms here and say that our fourth degree Taylor polynomial is equal to 4 over 2 factorial times x minus 3 squared plus 12 over 3 factorial times x minus 3 cubed minus 16 over 4 factorial x minus 3 to the 4th. And you can leave your answer just like that. If you want to simplify it some, you can, to get P4 of x is 2 times x minus 3 squared plus 2 times x minus 3 cubed minus, and then 16 over 24, that's 2/3 x minus 3 to the 4th. Okay, so that would be our final answer. For part B of this question, we want to find the x-coordinate of each critical point of G on the interval from negative 2.5 to 7, and then classify each critical value as a relative min, relative max, or neither. And we want to make sure that we are justifying our responses. So to find critical values for G, we know we're going to find G prime and then let that equal 0. So we did find G prime before. G prime of x equals f of 2x. G prime of x equals f of 2x. So we're going to let G prime equal 0 and solve. Where does f of 2x equal 0? So in order to figure this out, we want to know f of what equals 0, and then we can let 2x equal those things. So where does the function f equal 0? If we go back to our graph, and remember we are working on the given interval, f is equal to 0 at x equals 6 and also at x equals negative 2. And both of those values are within our interval. So those are both critical values. But those aren't the values of x that are going to make g prime equal 0. Those are the values that are just going to make f of x equal 0. So we need to set 2x equal to each of those. In other words, if we know that f of 6 equals 0 and that the 6 is really 2 times x, then that means that x equals 3. And if we know f of negative 2 equals 0 and the negative 2 is actually equal to 2 times x, then that means that x is equal to negative 1. So those are our two critical values, x equals 3, x equals negative 1. And again, both of those are within our interval. X equals negative 1 and 3 are critical values of G. So typically we would make a sign chart to check and see whether G prime is changing sign at our critical values. We have two critical values, negative 1 and 3. So if our x value is less than negative 1, so maybe let's just say negative 2, and we substitute that back into G prime, so I'm looking here, and we know G prime equals f of 2x. Maybe I'll write that here to be clear. F of 2x. Okay, so at x equals negative 2, G prime would be f of negative 4. And f of negative 4, if we think about the graph here, f of negative 4 is positive. So we've got our derivative positive here. It's equal to 0 here. It's equal to 0 here. Now, in between negative 1 and 3, let's try x equals 0. So we substitute 0 into g prime. That's f of 0, and we can see from the graph that f of 0 is negative. And if we try an x value larger than 3, like 4, f of 8 would be positive. So g prime there is positive. So our derivative of g prime, it is changing sign at negative 1 and at 3. And because g prime is positive, here we can conclude that g is increasing. And then at negative 1, that switches to decreasing. And at 3, it switches back to increasing. So this is a relative max. And this is a relative min. Now, sign charts do not count as justification on the AP exam. You have to justify your answer in a sentence. Explain it in words. Just showing the sign chart, even though that might be all you need to figure out the answer, is not proper justification. You want to communicate your mathematical ideas here very explicitly. So we will say G has a relative maximum at x equals negative 1 since g prime changes from positive to negative. At x equals negative 1. And then g has a relative minimum at x equals 3, since g prime changes from negative to positive. At x equals 3. Okay, so there we have completely answered the question. We have found the x coordinates of the critical points. We have classified each of those as a relative min or max, and we have justified our answer. Part C. Given that f prime of 3 equals negative 1/2, evaluate the integral on the interval from 1.5 to 3 of x squared times the fourth derivative of g of x dx. Here we have a product. It's not a product where u substitution is going to work. So the next thing we should be thinking is integration by parts. Can integration by parts be useful here? So the x squared, that's the polynomial part. The g, function g, we don't know exactly what type of function it is, but we're going to let that equal our dv. So our setup, we've got our u equals the x squared, and then the dv is everything else. G, fourth derivative of g dx. And we're going to take the derivative of u, so du over dx equals 2x, or we can just say du equals 2x dx. And then v equals, we're going to integrate here and knock that down to the third derivative. Now we don't need the plus c there because that's going to take care of itself when we set up our new integral, and also because it is a definite integral, so not necessary. Now our integration by parts setup is going to be the u times the v, so x squared times g triple prime of x minus the integral of v times du. And this new integral, although it is easier to deal with than the original, still is going to require integration by parts. So we need another integration by parts. And we've already used the letters u and v, so we want to use something different this time. I don't really like using something different, so I'm just going to go back and put little subscripts on my other variables here so that now I can just reuse the u and the v again. So this time my u is going to equal 2x. My dv is going to equal g triple prime of x dx. We'll take the derivative of u to get 2 du, and v is g double prime of x. Now this is a definite integral, so let me go back and make some notations, if you will. We know that this still needs to be evaluated from 1.5 to 3, and this also from 1.5 to 3. Okay, so now let's use our new integration by parts setup to expand on this. This is going to equal x squared g triple prime of x, 1.5 to 3, minus, now because there's a negative in front of this, I have to remember to distribute the negative to everything that's going to come next. So I'm going to put brackets here, so don't forget to distribute that negative. Okay, so now again we need to do the u times the v, so it's 2x g double prime of x minus the integral v times du. So 2g double prime of x dx. And I see that right there, that should have been a dx. So let's fix that. Okay, and that's looking good. This all still needs to get evaluated from 1.5 to 3. All right, so now we've got x squared, and g triple prime is the same as 4 f double prime of 2x. And then minus 2 f prime 2x times the 2x that's already there. And then we can go ahead and integrate the 2g double prime of x. When we integrate this, and I also don't want to forget that I have to distribute this negative, so this becomes a plus if I'm dropping my brackets. And then when we integrate, we get 2g prime of x, and the g prime of x becomes f of 2x. F of 2x. And all of this from 1.5 to 3. Okay, so now let's substitute in the upper limit of integration, the 3. 4 times 9 is 36, so 36 times, and then if x is 3, we need f double prime of 6, which is 3, minus 4 times 3 is 12, f prime of 6 is 2, plus 2 times f of 6 is 0. Okay, then we have to subtract, and we're going to substitute in our lower limit of integration, the 1.5. So 1.5 is 3 over 2. When you square that, you get 9 over 4, and multiply that by 4, you just get 9. So 9. And then it's f double prime of 3. F double prime of 3 is given in the table as 4, minus 4 times 1.5 is 6, times f prime of 3. F prime of 3 is given in the problem as negative 1/2, plus 2 times f of 2 times 1.5. So that would be f of 3, and we can see from the graph that f of 3 is equal to negative 1. Okay, this is a numeric answer, so you can just leave it like this, or if you want to simplify, you get 47. The last two parts of this question are not related to the graph or the table that we were given. For part D, it says, let the infinite series for a sub n from n equals 1 to infinity be a divergent geometric series. Does the series from n equals 1 to infinity of a sub n over n factorial converge or diverge? Explain. So it's not enough to argue that a sub n over n factorial approaches 0 as n approaches infinity, because that in itself is not enough to conclude that a series converges. We know that if this limit is not 0, then the series diverges. But if this limit is 0, it really doesn't tell us anything about the convergence or divergence of the series. So we have to try and prove this a different way. And I would say that most times when you have a factorial in your series, you're going to want to use the ratio test to try and show convergence or divergence. So let's use the ratio test here. And to set that up, we're going to take the limit as n approaches infinity of the absolute value of our n plus first terms. That would be a sub n plus 1 over n plus 1 factorial times n factorial over a sub n. We can simplify our factorials and just kind of rearrange things here. Got a sub n plus 1 over a sub n times, and then n factorial over n plus 1 times n factorial. So the n factorials there cancel out. And now I have limit as n approaches infinity of a sub n plus 1 over a sub n times 1 over n plus 1. So what do we know about a sub n plus 1 over a sub n? Well, we were told that a sub n is a geometric series. And it's always true in a geometric series that if you take one term of your series and divide it by the previous term, you get the common ratio r. And that's exactly what this means. It's a sub n plus 1, so the n plus first term in the series, divided by the nth term, which is the one that comes right before it. So this is just equal to the common ratio r. And because we know that this geometric series diverges, we know that r is, the absolute value of r is greater than 1, but we also know that r is constant. So in terms of taking the limit, it's really not going to factor into our limit. We want to focus on the part that involves the n right there. So this is equal to the limit as n approaches infinity of r times 1 over n plus 1. And again, the r is just a constant, so that's not going to affect the limit. N is approaching infinity, so 1 over an infinitely large number is approaching 0. And because this limit is 0, which is less than 1, we can conclude by the ratio test that the series converges. So therefore, a sub n over n factorial converges by the ratio test. And the last part of this question, now let the sum from n equals 1 to infinity of b sub n be the sequence defined by the following recursive formula. The first term is 1, the n plus first term is 1 plus 1 over n to the power n times b sub n. So we want the sum from n equals 1 to 3 of b sub n. Okay, so that's just going to equal b sub 1 plus b sub 2 plus b sub 3. And we know that b sub 1 equals 1. B sub 2, we're going to use our formula, and to get b sub 2, we have to let n equal 1. So we're going to let n equal 1 here, here, and then here. So b sub 2 equals 1 plus 1 over 1 to the power 1 times b sub 1, which is also 1. So that's 2 to the power 1 is 2 times 1 is 2. And then b sub 3 To get b sub 3, we're going to let n equal 2, so we'll have 1 plus 1 over 2 to the power 2 times b sub 2. So that's 3/2 squared, which is 9 over 4, times 2 is 9 over 2. Okay, so our third partial sum would be 1 plus 2 plus 9 over 2. And you can leave your answer like that, or you can simplify it further to get 7.5. Okay, then the next part says use the ratio test to determine whether b sub n converges or diverges. For the ratio test, our setup is to find the limit as n approaches infinity, absolute value, of b sub n plus 1 over b sub n. And that will be the limit as n approaches infinity of, and I'm just going to go back to my formula here for b sub n, which is this right here. So 1 plus 1 over n to the n times b sub n over b sub n. And we can see that the b sub n's will cancel out, giving us limit as n approaches infinity of 1 plus 1 over n to the n. And hopefully that is a limit that you recognize. That is one that you should have memorized going into your exam. That limit is equal to the number e, Euler's number. And e is approximately 2.72, so it is bigger than 1. And according to the ratio test, if our limit is more than 1, our series diverges. So we'll say, therefore, the series b sub n from n equals 1 to infinity diverges by the ratio test. Okay, that does it for question number 1. Moving on to question number 2. The differential equation dy dx equals k times y times the quantity m minus y has the slope field shown above. That should say below. Let y equal f of x be the particular solution to the given differential equation with f of 0 equals 1. Use Euler's method with 2 steps of equal size to approximate f of 2 in terms of k. For Euler's method, I find it easiest to use a table to keep the work well organized. So we want to start with a point where we know the x and y coordinate. And we have that point here. We know f of 0 equals 1. So here's our x, our y, 0 and 1. We're starting at 0. We want to approximate f of 2 using 2 steps of equal size. So we'll go on to an x value of 1 and then 2. That's it. That's going to be 1, 2 steps. And then we're going to have to calculate our slope at each step. So let's work with our slope equation a little bit here. dy dx equals k times y times the quantity m minus y. And we should be able to see from the graph what the value of m is equal to. So this horizontal asymptote right here, or the carrying capacity on our logistic differential equation, or the logistic equation, is occurring at y equals 10. So we know that the value of m is 10. So we can say dy dx equals k times y times 10 minus y. And in order to compute our slope, we only need the value of y. We don't need to use the x coordinate, just the y coordinate. So for this first point, we're going to let y equal 1 to compute our slope, and we get y prime equals k times 9, or just 9k. Okay, moving on to our next step. To get the y coordinate at the new point, we take the old y coordinate plus the step size, which is 1, times the old slope. So it's just 1 plus 9k. And that y value is what we're going to use to compute the new slope at this new point. So y prime equals k times y, which is the 1 plus 9k, times 10 minus y. And I'm trying to get my answer completely in terms of k, so I don't want to leave the y in there. I know that the y is 1 plus 9k, so let's rewrite that. It's k times 1 plus 9k times 10 minus 1 minus 9k. I'm distributing the negative there. Okay, so that's my new slope. Then I go on to my next step, and I take the old y value, the 1 plus 9k, and I add the step, which is just 1, times the slope, k times 1 plus 9k times 9 minus 9k. And that is my approximation. So we don't need to simplify beyond that. We could algebraically simplify this a little bit further. We also want to be really careful that we don't say f of 2 is equal to. We don't want to say equal to because this is just an approximation. We want to use the approximation symbol. F of 2 is approximately 1 plus 9k plus k times 1 plus 9k times 9 minus 9k. Okay, so you can go ahead and leave your answer like that. If you wanted to do a little bit of factoring, we could say that this is 1 plus 9k times 1 plus k times 9 minus 9k, like so. And if we knew the value of k, of course, we could just get a numeric answer, but we don't have that. So we will leave our answer like so. For the next part of the problem, we're asked to find f double prime of 0 in terms of k and y. So we're going to take the derivative of dy dx. dy dx equals k times y times 10 minus y. And we're going to find the derivative of that with respect to x. Because we're taking the derivative with respect to x, we need to use implicit differentiation here. And we're going to use the product rule. So I'm going to treat k times y as my first factor for my product rule, and 10 minus y as my second factor in my product rule. So derivative of the first will be just k. The derivative then also needs to be multiplied by dy dx, because k is the derivative with respect to y, not with respect to x. All right, so derivative of the first times the second plus the first times the derivative of the second, and the derivative of the second is -1 times dy dx. Now we're asked to leave our answer in terms of k and y. So we have to put something, substitute something in for the dy dx here, or our answer isn't completely in terms of k and y. But we know what dy dx is, so we can make that substitution. So it's k times ky times 10 minus y times 10 minus y again, plus, actually minus, k times y times, and then I'm subbing in the dy dx, so another k, another y, and a 10 minus y. And there we have our answer written entirely in terms of k and y. So this is our derivative in general, but we're asked specifically to find the second derivative at x equals 0. When x equals 0, y equals 1. Okay, so we can now simplify this further. D squared y over dx squared at, And here I can write x equals 0, I can write y equals 1, I can use the point 0, 1. There's different ways to write that. But I am going to now substitute 1 in for y. So we'll have k times 9 squared minus k squared times 1 squared times 9. So 81k squared minus 9k squared, 72k squared. So probably would have been more clear if it just said find f double prime of 0 in terms of k, because at x equals 0, we are able to eliminate the y from the equation. The next part, we're told the actual value of f of 2 is less than 4.6 is your answer to part A. So part A was where we estimated using Euler's method. Is that estimate an underestimate or an overestimate? And then justify your response. So again, we have this horizontal asymptote at 10, and we know that for our logistic equation, the solution to our logistic differential equation, it has an inflection point exactly halfway between y equals 0 and y equals 10. And until we hit that halfway point, the graph of the solution is concave up, and then after that point, the graph is concave down. So since f of 2 is less than 4.6, we know that we are concave down, or I'm sorry, concave up at that point. So in part A, if I go back, in part A, we were working on the interval from 0 to 2, and our solution curve is concave up that entire time. And because our solution curve is concave up, we know that our tangent lines are below the curve, giving us an underestimate. Okay, so our answer was an underestimate since f of x is concave up on the interval from 0 to 2. And again, it doesn't change from concave up until to concave down until we hit a y value of 5. And the last part of our question, let y equal g of x be the particular solution to the given differential equation with g of 1 equal to 12. So g of 1 equals 12 would be about right there. And let me just kind of sketch our solution curve. We're coming in towards this horizontal asymptote like so. Find the limit as x approaches infinity for the sine of g of x minus 10 over 2 times g of x minus 20. The limit of g of x as x approaches infinity is 10. That's where we have that horizontal asymptote. We're approaching that carrying capacity, whether we start below the asymptote or above the asymptote. So that part is 10. So if we're kind of substituting in here, we have the sign of 0 in the numerator, which is 0. And we have 2 times g of, let's see, again, g is approaching 10. So 2 times 10 is 20 minus 20. We also have 0 in the denominator. Now, in order to get full credit on this L'Hopital's problem, we want to make sure that we are showing that we checked the conditions for using L'Hopital's rule. So we do want to say the limit as x approaches infinity of the numerator equals 0, and the limit as x approaches infinity of the denominator So that's a really important step. A lot of times people skip over that step, but you need to explicitly write that down. That's what allows us to use L'Hopital's rule. So I'm going to say, therefore, L'Hopital's rule may be used. And in order to use L'Hopital's rule, we're going to find the limit as x approaches infinity of the derivative of the numerator over the derivative of the denominator. So we need to use chain rule. In the numerator, it's the sine of stuff. The derivative of sine of stuff is cosine of stuff times the derivative of the stuff. And then in the denominator, the derivative would be 2 times g prime of x. The derivative of the minus 20, of course, is just 0. And now we have the g prime of x canceling out. And as x approaches infinity, g of x approaches 10. So this is going to be the cosine of 10 minus 10, or the cosine of 0, over 2. And the cosine of 0 is 1. So we get 1/2 for our final answer. So these problems incorporated a lot of different concepts, some from the AB curriculum, some from the BC curriculum. Hopefully you found this helpful. Thanks for watching and see you next time.